Okay, guys, good morning again. Structure of this compound here is toluene. The methyl is by default in one position. The functional group of the common name is in one position. And then 2-bromo, 3,4,5-nitro, toluene. Yeah? It is a solid compound. Toluene is a liquid. Bromobenzene is a liquid. Nitrobenzene is a liquid. But all three together, it's a solid compound. Higher molecular weight probably adds to that. Okay, any questions before we get going? Any questions about lab this week? We're reducing your nitro to the amino. Everybody's using zinc, the zinc method. And before you do your reaction with your nitrochlorine, you need to make sure that it's pure and that, that it's pure. You don't want to be using impure starting materials, or you're very likely not going to get a good product. It'll just get worse. Any questions about lab? Okay, so we're looking at EAS, and we looked at substituent effects. Those included activation, deactivation, and also, for example, is this going to be more reactive towards EAS or less reactive towards EAS than benzene? What do you suggest? More reactive than benzene or less reactive than benzene? But we still have three open positions that we can do a substitution at. Because in EAS, we replace an H with a I've got a strong deactivator, a weak deactivator, and only a weak activator. So these two sort of cancel each other out. A weak deactivator, a weak activator, and you're left with just a strong deactivator. Yeah. I suggest it's probably less reactive than benzene. Okay. Another question though. If we were to do a reaction here, maybe we wanted to chlorinate this, chlorine and aluminum trichloride, where would the chlorine go? Would it go here? Because these three positions are different. Would it go ortho to the bromine? Would it go meta to the bromine? That's also meta to the bromine. Both of these are meta to the bromine.
Should go
Yeah? Nomenclature video? Where would he go? That's directing effects. Okay? And what did we say about directing effects? Well, let's continue that. Because if we just had a methoxy group, what type of director is a methoxy? Orthopara. So a new group by an EAS will go ortho or para, yeah? And you have this ester group. It's a meta director, right? So the new group would go meta as the major product, okay? Directing effects, right? Groups 1 through 3 are ortho-para directors. Group 4 is meta director. Okay, down below, bromine would be, what type of director is bromine? Orthopara, right? The iodinate, you're going to get two major products over here. Which one might be major of the major? What, para? Because going ortho, it does have to come next to the existing group. Sometimes para is kind of even more favored, but in general we say these are the two major products. Compared to the meta here, you would get very little meta. Okay, why is that? Well, it all has to do with stabilizing the sigma complex intermediate. Let's look at that. Here, this is toluene, methyl group. If we do an EAS reaction and this pi bond attacks the electrophile, I don't know how they're really moving their arrow. I reckon they're moving it way up here to make bond E, leaving the bottom carbon positive. Resonance structures. You got to be able to draw resonance structures here. Okay? I agree. Resonance, resonance. That's it. No other resonance. You cannot do any resonance with the methyl group. It has no lone pair. It has no p orbital, etc. Okay? But is there anything good about these three resonance structures for the intermediate? Yes, right here, we said this before one day, right? We can see that the methyl here, the substituent, stabilizes the cation there. By how? Induction. Inductive donation. If you do a para attack, or I would rather say if we add the electrophile, para, electrons come out here, then making it the para carbon being bonded to the E, leaving plus here. Make sure you get your arrow movement right. Resonance, windshield wiper down. Okay. We can windshield wiper up. Resonance structures. But again, look right here. We get a resonance structure where the positive is stabilized by that group, methyl. What if we do a meta attack? Well, you can look through this. You get positive charge here. Resonance here. Resonance here. Okay. Do you ever get the good resonance structures where the methyl is right on the positive carbon? No, never. So the sigma complex is not stabilized like this. And so that pathway is not going to be preferred. These two pathways get the extra stabilization by the substituent. That's why the reaction prefers ortho-para. The intermediate, if it goes ortho or para, is stabilized. Thus, the transition state leading to that intermediate is typically lower. Over here, it shows an amino group. Same sigma complexes replace methyl with amino. Bam, bam, bam. But since the amino group has a lone pair, we can do resonance. Right? Bring the electrons down, make pi bond. So we get an additional resonance structure with the amino group. Or any atom with a lone pair, we can get an additional resonance structure. If we do a para reaction, sigma complex, positive, resonance structure, resonance structure. Now they're doing, at this, when you get to here, we can either bring these electrons down to give that, or instead of doing that, you could have windshield wipered those up. And that would have given the one on the right. The way they're doing it, they're going from here to here. I would probably have suggested maybe saying an A. The A arrow gives this structure, and then maybe draw another resonance structure from here, and then show maybe this and call that maybe a B arrow and show that one here. That's the way I would have done it. But again, right here, positive on that carbon with the group, resonance structure. But if you do a meta attack, if you look at it, the positive never falls on that carbon. And so you can never do the additional resonance structure. So the intermediate is not stabilized by the additional resonance structure. And so why would the reaction form that intermediate? It's not. It's going to form either this one or this one preferred. Either ortho or para preferred. More stable intermediate, yeah? Thus lower transition state energy leading to the more stable intermediate. Now on the other hand, below, the nitro group is what type of director? Meta. Why is it a meta director? Well, look at ortho. Positive, positive, positive. The positive does fall on the carbon with the group. But is this a good thing in this case? No, it's bad. Group 4. The atom that's in a group 4, what do we know about that atom that's bonded to the ring? Electron core and no lone pair, right? Okay. Since there's no lone pair, you can't do resonance here. But since it's electron poor, what does that make? What does that create here or lead to? It makes it bad, okay? Partial, you don't want a partial poor atom next to a positive, a partial poor atom. It's a bad situation. You also get that repair attack. In this case, these are bad. If you do meta attack, the positive never falls there. And so you don't get the bad. Now there's nothing really good about it. What's good about it is you don't get the bad. So which route would you rather go? A route with the bad thing that happens, or the route with just nothing?
The nothing.
The nothing is going to be better than the bad. And so it prefers to go meta. Okay? You need to understand, be able to draw resonance structures. Well, this is the explanation of your directing effects. Looking at things that can donate by resonance, things that donate by induction, and then a group 4. Now, there's one. Actually, the halogens are peculiar, like a chlorine. What type of group is the bromine here? Let's do bromine.
It's 3.
Group 3, is it an activator or deactivator? Deactivator. Why is it a deactivator?
Because it's green.
But it can donate by resonance.
Right. But it's still like the net
Net,
is that it's going to pull away.
it's a
rather
net
than to-
withdrawer because it's more greedy than it will, okay?
Give.
Yeah. Okay. But it can donate by resonance. So why is it a deactivator if it can donate by resonance? Back up here. What if this was like a bromine with a lone pair? Could you do resonance structure? Yes. You do resonance structure. Wouldn't that stabilize and yeah. But that just tells you it's an ortho pair director. Even though you can do resonance structure, it's still a deactivator. Because its net effect is withdrawing. And if we put a bromine down here, which is the strongest withdrawer? A bromine that cannot donate by resonance. See here, the amine does not donate by resonance. Okay? Or bromine with resonance. Which one's a stronger withdrawer? It's a stronger withdrawer. Okay? And if that's a withdrawer, is it going to help when we form a positive in the ring? No, it will hurt it. This hurts more. This has some donation. But just because it has donation doesn't mean it's an activator. It only means it's more active than this. The net effect is bromine, is withdrawing. Ultimately, group 3 is a little bit of a conundrum. It's an ortho-pair director because it can donate by resonance. But it's a net withdrawer because the major effect is withdrawing. It's a net deactivator. So what you cannot say are all activators are ortho-pair directors and all deactivators are meta-directors. You can't say that. Only the strong deactivators are meta-directors. Okay, directing effects, we can look at these. Multiple substituents, reinforced direction. Remember I asked you about this one with 3 substituents? Where would it go? Mike should have left that up there. What is that, a methyl group? What type of director is the carboxylic acid? Meta director. The methyl group? Ortho. So let's do this. This group is directing where? Meta? Or there, but that's identical position, right? Where's this group directing? Ortho. Okay. I'll do this with an X. Ortho or para? But the para position is blocked. And usually you're not going to do anything there. You can sometimes do some funny chemistry there. But usually in an EAS, we're replacing an H, right? Look at the EAS mechanism. So where's it going to go? Right there. And so if you fluorinate this compound, you would expect to get the product shown. And that would be reinforced direction. The 2 groups are directing to the same position. Everybody see that? Opposing direction. Here's a statement. The strongest electron donator directs. It's the one that's going to direct. Because it will stabilize the intermediate better. It's able to stabilize intermediates better, and so it's going to kind of rule. For example, here we got a clear winner. What type of director is this? Ortho-para. How about this? Alkyl group, methyl, ethyl, propyl. Group 2. Okay? They're both ortho-para. So this group is directing ortho, and this group is directing ortho. So it's opposing. Where's it going to go? Which one's going to ultimately direct? The strongest donator. Which one's the strongest donator? Methoxy, group 1. Group 1 is stronger than group 2, and group 2 is stronger than group 3. Okay? So it actually directs, and so if you try to sulfonate this compound, you're going to get the sulfonic acid next to the methoxy group. Ortho to the methoxy. The para position is blocked, and so that would be your major product predicted.
What if both of them were strong electron donors? Would it be like a mixture of both.
Okay, there we had a clear winner. Let's look down here. What if there's not a clear winner? Both of these are ortho-para. This is directing ortho, para is blocked. This is directing ortho, para is blocked. Okay? Well, what type of directors are these? They're both group 1. And they're both pretty darn similar. So, which one's going to direct? It's not going to be a clear winner. You're going to get kind of, okay? And so I showed two major products. One being ortho to the methoxy, and one being ortho to the phenol. The OH group of the phenol. So, does that answer you? You're going to be more prone to getting mixtures, because you don't have a clear winner. Not a clear winner. And so this reaction is not going to be as nice, not as clean. You're going to have to, you'll get a mixture, you're going to have to spend more time purifying it. And ultimately, after you separate these yield of a single one may be fairly low. How about this example? Cyano group is a metadirector. Chlorine is ortho-para. What product is favored? Actually, you got three favored products. Which one directs? The cyano group or the chlorine? The stronger director. Now, that's not an activating substituent, but it's more activating than that one. It's group 3. Yeah. And so, how does it direct? Ortho and para, all three positions. Is there any one of those where you say might be for more or less? They're all three theoretically favored. Is there something we could say about one of them?
Or the ortho.
Which one?
The one that
Yeah. The bromine coming in between the two existing groups may be a little sterically hindered. The approach getting in there. Maybe the second or third, maybe one of those would be more predominant. But this reaction is likely kind of messy. You're not going to get chemoselectivity. Well, or we could even say regioselectivity. It's not going to be that regioselective. Show the product, the next, we got two down here. First one, show the product here. This is vanillin. It's fake vanilla. You eat vanilla wafers, Nilla wafers. And you can look at the ingredients, it says vanillin. Basically, natural vanilla is vanillin, but this OH is hooked to a saccharide. Okay? But in your mouth and in your body, that's readily cleaved, and it produces this. Okay, that's natural vanilla. But it is going to have maybe a little bit different taste, more genuine taste. But chemists figure that out. Instead of giving the natural with the saccharide, you can just use that molecule and get very close taste. Artificial vanilla. But it's so that's a molecule. You can extract it out of vanilla wafers and then do some chemistry on it. Okay. Looks like we're trying to brominate it. What's going to be the product? About that there. Okay, what type of director is this? This? And this? Okay. Where's this group directing? Here? block, so directing there. Where's this group directing? Ortho, and para. Directing there. Where's this group directing?
It's not.
Meta block here. Two groups are directing there. Could you get a little bromine here or here? Possibly, but I have an argument that this is going to be the preferred site. And indeed, that's a known reaction. In fact, I think we've done that here in the lab before. I think I used to have that as a lab. Halogenation of aniline, and indeed you get that product. After you purify, you may get some of the others as minor components, but you can recrystallize it or something, or do some type of purification. Get that as a major product, as your theory would predict. How about below? This has two rings. What are we trying to do, a nitration? Question, which ring is going to be nitrated? What type of director is this? Strong activator. What type of group is this? Weak activator, group 2. So which ring is more reactive? This one. Now, someone could make an argument that the effect of this is felt not only here but into that ring as well. But then I would have to come back with another argument. But I think it's, let's just safe to say, this ring has the activating group, the stronger activator. Okay? So, of this ring, where's the new group going to go? What type of director is it? So he's going to go ortho, or what? Para? But the para is blocked. So where's the nitro going to go? I'll just draw a product like that. Yeah? It would be nitrating that ring ortho to the methoxy group. The methoxy group is the stronger activator, and it's an ortho-para director. Questions about that page?
What about the other ones that is position?
Do what?
The others?
They're equivalent. You could have put the nitro in either position. It's the same compound. You name it, it's the same compound. Symmetry. Okay. And if you look at the tan sheet, we sort of stopped between C and D. C was sulfonation. After sulfonation, we looked at active substituent effects. Now we need to go back to D, which is what? Friedel-Crafts, and that's on the blue sheet. The reason we had to first look at substituent effects is because when you do Friedel-Crafts, we have to consider substituent effects. But now that we know substituent effects, we can have this discussion. Friedel-Crafts, we're going to see alkylation and then acylation. Both of these, we're putting a carbon on the ring. For example, here, benzene can react with isopropyl chloride, with aluminum trichloride catalyst. Okay? And we can make this bond here. Carbon-carbon bond formation. Benzene to carbon. We haven't done that before. We did benzene to bromine, or benzene to nitro, or benzene to sulfonic acid. This reaction was first described in 1877 by two chemists, Friedel and Crafts. Okay? And usually when reactions are named according to the chemists that discovered the reaction and developed the reaction, usually the reaction is pretty important. Okay? So it's one of the top 10 reactions in organic chemistry. Okay? There's about 20 top 10 reactions you need to know about. Okay? largely because historically in organic chemistry, particularly early on, back in the 1800s, it was very hard to make carbon-carbon bonds. It was much easier to make carbon-nitrogen or carbon-oxygen type stuff. And carbon-carbon bonds was always difficult, and when this came along, people really took notice, like, well, okay, great, this is a great advance here. We can start making carbon-carbon bonds to ring bond into a carbon. Now, the electrophile here is our good old friend, a carbocation. Have you ever made carbocations? Well, whatever way you've ever made them, you can do it here and you can get an EAS reaction. Okay? And you already know many ways. A new way, though, which is kind of more common here, is can this thing just ionize and make a carbocation? We need to get to this carbocation, and then the ring can attract it. Can that just leave? Chlorine's not a great leaving group. It's okay. Secondary cation. It could. It's not going to leave easily. In organic 1, we showed a way. How do you make halogen a better leaving group? Usually you don't have to, but what do we do in organic 1? There was also a chemical test in lab, which we may not have done. We complex the halogen with silver ion. Silver nitrate test.
Yes.
And, okay. And the silver ion we call the Lewis acid. Okay. Pull out the handout. You didn't sell the handout back, did you? Okay. Don't sell your handouts back. Keep your handouts. Here we're going to complex the halogen with the Lewis acid. Okay? And this is aluminum trichloride. Does the aluminum have a lone pair? No, it has 3 valence electrons. They're all there. There's no lone pair. It has an empty p orbital. No octet. Just like boron we did with aromaticity, and I showed a boron. Same thing. It had an empty p orbital. This has an empty p orbital. And these electrons will add to it. We also used, well, we used FeBr3 in our mechanism, but you can also use that when you chlorinate. Chlorine and aluminum trichloride. Okay? Because when you chlorinate, you got chlorine, one of these chlorines adds to the aluminum. Again, in the mechanism, I think I did a bromine added to iron. The chlorine adding to aluminum, the same thing. But we're doing that here. And that's going to give Cl. Now bonding to aluminum, I'm just going to condense these Cl3. But the aluminum is now minus. And the chlorine is what? Positive. Now the chlorine really wants to leave. I got to get my electrons back. It can take them back from aluminum, but you would just be doing this, right? So that is an equilibrium. But it can take the electrons from the carbon. And what would that give? That plus what? I hate to show this condensed, but a book may show it. Be AlCl4 would be minus, right? Okay? You need to see that structure. I mean, all it is lone pair here. It remains minus there. There you go. Now you do your ES mechanism. Which carbon is this going to? They're all the same. We don't have any substituents. So these electrons attack here, yeah? Do I need to do the ES mechanism? And we can get bond to the isopropyl. Positive here. There is an H there, right? Every carbon has an H. Sigma complex, resonance stabilized. Okay? And then what's the next step? See, that's where I should have drawn this out because now we need to use it. We draw this out. See, aluminum's not happy. You can't make boron and aluminum happy. Okay? So now the aluminum's like, okay, chlorine, you and your electrons go, and the chlorine's like, okay, I'll go, I'll break away from you, and I'll go bond to the H, and then these electrons can move here. And what does all that give? That gives product plus HCl. What else is formed? Your Lewis acid catalyst is reformed. Same EAS mechanism, it's just we had to see how we form the electrophile. And the electrophile is the carbocation. And we added an alkyl group. Isopropyl is an alkyl. Friedel-Crafts alkylation. This reaction works with primary, secondary, tertiary sp3 halides. Now this refers to the alkyl group. I should put here alkyl halides. Okay? Chlorine is most common because the reaction does work, and chlorine is also the cheapest. Okay? Now when we do regular SN1, SN2, usually we use bromine or even iodine, better leaving groups. But see, when we do that, we don't use a Lewis acid often. We just get it to ionize. Okay? But here we're using the Lewis acid, and when it complexes with that chlorine, it really makes it happen. Now, this is questionable because if you look at the mechanism, we're forming carbocation. So how does it work with a primary halide? Are you going to form a primary carbocation? I would want you to be very suspicious of that. And the mechanism may be a little bit different. It may be more like an SN2 type mechanism. Okay. Just be very suspicious of that. I'm never going to show you this reaction. In my example, what type of carbocation did we form?
Secondary.
Secondary. So yeah, you're not going to get me to show you the primary carbocation. It does not work when the chlorine or the halogen, we can just say chlorine most common, is on an sp2 or sp. Now both of these are sp2. Doesn't work with these as the electrophile. You can do a Friedel-Crafts with chlorobenzene, but they would be reacting in the ring. You're not replacing this chlorine. In organic 1, we said plenty of times, you're not going to make carbocations on these types of carbons. Okay, do you know any other routes to carbocations? Can you make a carbocation from alcohols? Yeah, you did that plenty in organic 1. We've done it in organic 2, yeah. And we've typically used acid. You can do mechanism for this, protonate, ionize, and we can make carbocation. Okay. You can also do this with a Lewis acid, and with alcohols, BF3 is a common Lewis acid. And so it's an NTP orbital, this complexes with the boron, and we get to this here. And now the oxygen has become positive, and now this can leave. And what does that produce? It produces those two. So that's using a Lewis acid instead of a proton acid. Okay. Have we ever made carbocations from alkenes? Yeah, the very first reaction I did in organic 1 was an alkene reacting with like HBr, right? Yeah. So these electrons just break away, right? Hinge out, make carbocation there. The same carbocation we made above, except above we made it from an alkyl chloride complexing with aluminum trichloride. Okay?
Is there a benefit to using a Lewis acid over just like a regular acid and alkene? Or does it just depend on what you're starting with?
Basically, you got many options. You can, if you, however you can make a carbocation,
Okay.
the ring will happily react.
Okay.
Okay? But not always, because some rings don't react. And let's see. Friedel-Crafts does have some limitations. First off, it fails with strongly deactivating substituents. And strongly deactivating substituents are also called metadirectors. Everybody agree with that? Yeah, it fails with metadirectors. If you take nitrobenzene and try to do Friedel-Crafts alkylation, the same we did on the previous page, you're going to get no reaction. Now, you can come in here and brominate nitrobenzene. Go meta, right? You can do sulfonation of nitrobenzene. But for some reason, with group 4 metadirectors, Friedel-Crafts doesn't work. And you can think about perhaps why, but we sort of know that. It doesn't work. All right? And sometimes Mother Nature's hard to figure out. But, okay? So this works, and that doesn't. So, you can't do Friedel-Crafts with metadirectors. Friedel-Crafts also fails with anilines. You cannot take an aniline and do this and it won't work. Now this we can understand. You ever seen 2 rules? Rule 1 is follow mama. Rule 2 is seek rule number 1. Well, that's really what this is. Because the second one is really C number 1. First, you have to understand that this is slightly basic. Even though it's conjugated, it has some basicity. And guess what this does? Okay? Instead of this lone pair coming here, that lone pair here. And what does that lead to? I'm just going to show the and now, that looks like a strong activator, but what does it look like now? Now it is an electron poor atom with no lone pair. And now it's what? Now it's a group 4. And what do we know about group 4?
They don't react.
Refer to rule number 1, right? And didn't I show you this before? Said be careful about it. Remember this note written over here on the left? And it pointed you down here. The amino groups, how do they exist in the presence of proton acid or Lewis acid? They exist with a positive charge. And we've turned them into a strongly deactivating group. And so, thus now we refer to rule number 1. Now, it does work with oxygen. If there's an oxygen here, it'll do a Frito-Crafts. Apparently that long hair won't coordinate as well as the amino. But isn't nitrogen a stronger base? Yeah. You can also do Frito-Crafts with amides. Okay? Because this is less basic. You can do phenols, anisols, and even here. You just can't do free anilines with the free amino group. Another problem with Frito-Crafts is rearrangements. And this is where I may have to show a primary carbocation, although there is perhaps another way to do this. I'm not going to do it the other way, but look at this reaction here. You take this with, what is this, 1-chlorobutane? What are we doing here? Can I just complex this with aluminum trichloride? Right, it complexes. And then, okay, don't cringe. I know you're going to like groan a little bit, but if this just leaves, what do we get? Okay, ooh. Primary carbocation. Then the ring attacks it. Which product would we get? A? Yes, you should see that. Okay. But guess what? We actually get 65% more of the lower product. Why? What are carbocations prone to doing?
Rearranging.
Yes. These electrons break away. That's a looping arrow. Let's hydride shift, right? And what does that give? Secondary carbocation. Now the ring attacks that carbon, the secondary carbon, and we actually get a greater yield of that. It is known to give a mixture, but a rearrangement. Now, if you wanted it to rearrange, then good for you, and you got that. But if you didn't want it to rearrange, you're stuck with a lower yield, and you have to purify out something that's more predominant. Okay? But again, this is carbocation chemistry. Carbocations are prone to rearranging. Now, later on, we'll see a better way to make compound A. That's why I labeled it as A. Another problem with Frito-Crafts is polyalkylation. We do this reaction, we get what? Isopropyl benzene? But it'll react again. Because which is more reactive, benzene or isopropyl benzene towards an EAS? Why isopropyl benzene? Because isopropyl, the carbon, sp3 carbon, is an activator. It's a weak activator. Okay? More reactive than benzene towards EAS. What type of director is that isopropyl? Ortho, para, or meta? Okay. I'm showing para. We could say plus ortho. There might be ortho here as well. Well, which is more reactive? Isopropyl benzene or diisopropyl benzene? Yeah. And which is more reactive? To tri or di? Okay. So what happens here, if you try to just do one equivalent, and this reaction proceeds maybe 10%, and you got 10% product and 90% of this left, well, this product starts reacting with the reagent. And benzene's like, hold on, I want to react. And the product's like, sorry, I'm going to react more. And before you know it, and then this gets formed. And then it starts reacting with the reagent. And you're like, stop, I only want benzene to react. They won't listen to you. They react faster. And you end up with polyalkylation. Okay? Ever heard of, what does a parrot say? Polly want a cracker? This is polyalkylation. Okay? Now, don't tell anybody I told you this. One tricky way to keep this from happening is use a huge amount of benzene. That way, even though you start producing these, if there's a huge amount of benzene, it will still sort of react. But you can only do that when your starting material is very easy to get rid of, like with benzene solvent. You can just boil it out. Okay? A lot of times you can't do that. All right, there's a number of limitations. We'll deal with these moving forward when we look at acylation. Acylation is not going to have as many limitations. Next page. Okay, see some of you in lab. We're meeting upstairs. Always, unless we say otherwise. Have a good day, guys. We'll have our first quiz soon. Soon, in the next few days, rather than later. I just reminded you that we will have quizzes.
So like we're getting close to it,
Yes.